Hey learners, and welcome to the video walkthrough for the projectile motion test version 2. So here we had two projectiles, one fired horizontally from a height that was 10 meters off the ground, and it was fired with an initial velocity of 20 meters per second. And the other ball was fired straight up with an initial velocity of 10 meters per second. And the first graph is all about ball one, the ball that's actually fired. And we are to sketch the vertical and horizontal position versus time graph. So horizontal versus time, and then our vertical versus time. So how does this object move through both of those dimensions? Well, through the horizontal, it's going to move at a constant speed. So your graph would need to be a straight line with either positive or negative slope. I didn't say that right was positive and left was negative, but you are looking at 2 points for that graph, and you got those 2 points if it was linear. The vertical graph needs to be a parabola. Make that a parabola. That is concave down and is initially flat. And your point breakdown would reflect that. So you got plus 2 points if you had a parabola. You got another 2 points if it's concave down. And you got another 2 points if it was initially flat. And the reason it needs to be flat initially is because it's a horizontal projectile. All of that initial speed, that 20 meters per second, is in the horizontal, and vertically it has no initial velocity. And so that means initially it needs to be flat. For part B, now we're calculating the fall time for ball one. And so time being governed by the vertical dimension, we need to look at the vertical position versus time graph, kinematic. And we can eliminate v initial y and t. Those are multiplied together, and v initial y is 0. So the ball is going to land on the ground. It's going to start 10 meters off the ground. And then 1/2 our acceleration if we assume we're on Earth, -10, and then t squared. And then from here, you could have either graphed, and you could have plotted this graph and solved for that time right there when it actually hits the ground. Or you can solve this algebraically. So subtract 10 from both sides. Half of -10 is -5 meters per second squared times t squared. Divide both sides by -5. And your last step is to square root both sides. So you get t is the square root of 2 seconds. And each step along the way here earned you points. So you got plus 2 points for showing the correct kinematic to use, plus another 2 points for showing the correct substitution of values, and then plus another 2 points for the correct answer. Now, part C is about the fall time for ball 2, the ball that is shot up into the air. How does that time compare to ball 1? And so you could have gone through and solved for ball 2's fall time pretty much the exact same way. But it's a little different because it both starts on the ground and ends on the ground, but it has an initial y velocity. And so you need to solve for, and then ay, we have that, it's 10. Yeah. And so we can go through and we can solve for t. And again, you could have done this graphically, or you can do it algebraically. Here we can divide every term by t. Cancel, cancel, and then 0, 0. And that leaves us with 0 meters. We don't need to write that 0 anymore. So 10 meters per second minus 5 meters per second squared times t. And then we're just solving, and, algebraically. I could add 5 to the other side and then divide by that 5. But you get for a fall time of ball 2 to be 2 seconds. And that's got to be greater than the fall time for ball 1. Now you could have also thought about it like this. Ball 2 is shot up into the air at 10 meters per second, and its acceleration is negative 10 meters per second per second. So each second you do this to that. So at 1 second, my velocity is 0. Which means another second later, your velocity is going to be back to negative 10 meters per second, and you're going to be back down to the ground. So if it took you 1 second to get up, it'll take you 1 second to get down, 2 seconds, and that's got to be bigger than square root 2. So there's a couple of ways to think about that. But the point breakdown, +2 for selecting greater, and then +2 for a correct explanation. On part D, now we're sketching the horizontal and vertical velocity graphs for ball 1, the horizontal projectile. And so Vy, Vx. And so horizontally, that ball is going to move at a constant velocity. But then vertically, the ball is going to get faster and faster. So it is linear with negative slope to denote the negative acceleration. And it also needs to start at 0 because v initial y was 0. So that graph was worth 3 points. Over here, you got a point for saying it was flat, and then +2 points for saying it was not at 0. So at some at non-zero value. How far away does the ball land? So this is a range question. Delta x is vxt. And as long as you use the time that you solved for in part B, even if that time was wrong, you still got credit. And then Vx is that initial velocity, that 20 meters per second. So this is the time you got from part B. This is 20 meters per second. And as long as you did both of those things, you didn't even have to multiply them together. As long as you showed how to get it, I gave you the full credit. And then how much time delay should there be so that they both hit the ground at the same time? So ball 2 should be fired first because it takes longer. And the delay that you should have is 2 minus square root 2 seconds. So each of those things got you a point. And for this free response, there were 30 points available. And that's your walkthrough for test 2.